Hi, today we're going to look at a capacitor. So the first thing we need to know is what is capacitor. Okay, capacitor have been used for years, maybe tens of the years. Okay, in electronic circuits, the main purpose is to store electrical charge and also to discharge. But if you look at the word charge and discharge, we have another electrical device also do the same thing, which is the cell or the battery. But the difference between them is battery discharge or charge based on chemical reaction, but capacitor based on the creation and the collapse of electric field between two conducting parallel plates. Alright, that's the difference. And one of the main difference in a capacitor over a battery is that the charging and the discharging of a capacitor can be much faster compared to a battery. That's why we can use capacitor as oscillating equipment in a circuit, but not battery. Alright, so first we look at the capacitor. The purpose is to store electrical charge. Okay, to store electrical charge. Well, that is to store, but we can also to release, which is called the discharge. To store is to charge, to release is to discharge. So that is the capacitor, the purpose of capacitor. So the basic design of a capacitor is you need to have two parallel plates. Okay, that plates are conductors. Alright, so it's as simple as that. Two parallel conducting plates. So this conductor can be made of mostly aluminum, but it can actually theoretically any metal. Okay, any metal that conduct electricity. So when you connect one of the plate to a positive terminal of a power supply and another one to the negative terminal of the power supply, you set up electric field in between. Okay, so the surface will be charged. So this one will be charged positive and this one will be negative. So when you have a potential difference between two parallel plates, you are creating electric field. Okay, so that electric field will stay in there as long as the charge on the plates exists. Okay, even though you take away the battery. So that's the beauty about this. And theoretically, again, the electric field or the charge that is stay inside the plate will be theoretically forever. But the problem is there are leaking here and there that cause the capacitor to have this self-discharging based on internal leakage. Alright, so we don't have any ideal capacitor, only in theoretical. Alright, so that is the design, basic design of a capacitor. So the symbol of capacitor, well, is very easy. It looks quite the same as a battery, except these two lines are the same length. There are so many symbols used in electronics. This is one of the symbols without telling you which one is a positive and negative terminal. But some have this symbol. Okay, sometimes they tell you this is a positive, or you might have this darkened. Okay, thicker plates compared to the another one. Okay, darkened. This one is positive, and another one will be something that looks like this. So this one will be positive. So this one positive. All right. So some capacitor don't have polarity, like ceramic type of capacitor. Those are operating at high frequency, so normally they don't have polarity. But for this type of capacitor, the one that we're looking at, we have to emphasize the polarity. Why polarity is important? Because when you charge a capacitor, you don't want to charge it wrongly. Because when you charge it wrongly, the capacitor might get overheated and some chemical inside that insulate the conductor might get evaporated, and then it cause pressure and compromise the packaging of the capacitor. It might cause a little bit of explosion. Okay, so that is capacitor, basically to store charge and the design, and this is the symbol. Alright, so that is a basic design for our capacitor. So what is the purpose of capacitor? The purpose of capacitor in electronic is basically to actually delay to change the phase in between the voltage and the current. That is, if we are talking about AC current, and we can actually use it to do something like an oscillating circuit in a DC circuit. Okay, and also at the moment we might have some sort of so-called supercapacitor, which is actually used to actually replace battery. Okay, remember what I said just now? The charging and discharging of capacitor is much faster, okay, compared to chemical battery. And theoretically, there is no number of cycle of charging and discharging of what we call the capacitor. So it's actually much more reliable compared to battery. So far, the best battery in the world, which is based on the lithium-ion polymer design, they have about 500 to 1,000 cycles. Okay, you can charge and recharge for about 1,000 times. But theoretically, for capacitor, there is none. Okay, there is none. Okay, so one is more reliable. Okay, more reliable. It does not contain any chemical inside. Number two is it can be actually release the charge much faster to achieve high power output. Okay, battery cannot do that. Okay, battery cannot do that because battery is based on the chemical reaction. How fast a chemical reaction occur, that is how fast the charge is released. But chemical, you can actually in a split second release all the energy and create high intensity of energy output, which is very good in the usage of laser production, okay, laser light production, and maybe in weapon, EMP, okay, electromagnetic pulse weapon. Those are the things that can be used for capacitor. All right. So the next thing is we're going to look at the definition of capacitor. Okay, capacitor. The ability to store charge by a capacitor is called the capacitance. Okay, capacitance. The symbol we use is C. All right. Now, let's assume we have a battery with voltage V, and then it is connected to a ideal capacitor. Now, why would I use the word ideal? When you say ideal, there's no resistance. Okay, there's no resistance in the capacitor. Now, let's assume again, when you connect the capacitor to a cell, you actually accumulate charge. Because this plate here is connected to the positive terminal of the cell, so it's accumulated positive Q of the charge, and the one connected to the negative terminal will accumulate the total charge of negative Q. So now our capacitance, okay, is defined to be C is equal to the ratio of the charge on a plate across the voltage. Okay, so now we have Q over V. So you see, this is the definition of our capacitance. So the unit for capacitance is now coulomb per volt, okay, or CV -1. But coulomb per volt actually is simplified to be farad. Okay, farad. So 1 farad is the charge, okay, contains on a plate across a voltage of 1 volt. Okay, that is 1 farad. So the symbol used is big capital letter F. So that is the basic definition for capacitance. So we will write down the statement or the definition of capacitance. So capacitance C is defined to be the ratio of the charge on the plate to the potential difference across the plates. Okay, because you got more than 1 plate. So the C is equal to Q over V. So when you are asked to define, that is the definition for capacitance. Alright? So the next thing you want to look at is, there is another formula. Other than calculating, divide the charge by the voltage, you get the capacitance. We have one formula that is actually more geometrical or more physical. Okay? But it only applies to parallel plate capacitor. Okay, parallel plate capacitor. parallel plate capacitor is the capacitor that we talked about just now. Okay, parallel plate capacitor, you need two plates like that, another one like that, and there are two terminals. Okay, now if you look at this one physically, or the geometry is, we have surface area A, and then we have distance between the plates, we call the separation. Okay, and this is D. Okay, and from experiment we discovered that the capacitance is actually directly proportional to the surface area A. The larger the surface area, the larger the capacitance. And then it is also discovered that if you place the plate nearer to each other, you are actually increasing the capacitance as well. So when we combine these two, we have directly proportional to A over D. And when we change it into equation, we're going to get a constant here. Okay, a constant K A over D. And this constant is, the K is actually equal to something that we call the permittivity of a vacuum multiplied by the relative permittivity of the medium. Okay, so that relative permittivity of the vacuum of the medium inside there is another concept involved, which is called the dielectric. All right, so all this value here depends very much on what material you put in between the parallel plate, so that the value of the capacitor, the capacitance of the capacitor can be changed. All right, so that is our epsilon R. So you already know the epsilon naught. This one is the permittivity of vacuum when we study electrostatic force. This one is 8.85 10 to the power negative 12. This one is farad per meter. And then this one here is called the relative permittivity. Okay, so this one is related to the material use. Okay, material use. The purpose of the material used in between the parallel plate, number one, of course, is to avoid short circuit. Okay, because when you place them too near and you try to bend them, there are possibility that they are touching each other and cause short circuits. Okay, and the charge just neutralize each other. That's number one. Number two is, if we look at this equation, if the value of epsilon R is large, then we can achieve a high value of capacitance. That means the ability to store charge will be increased. That is the beauty about this thing. So now if we put together the equation, it becomes C equal to epsilon naught epsilon R A over D. So this is our general equation, but it only applies to capacitor that have a shape like this. Okay, the shape doesn't mean the shape must be rectangular or square. It can be any shape that you have a formula to calculate the surface area. It can be two circular shape. Okay, two circular shape. So that is a formula to calculate, another formula to calculate the capacitance, but applied for parallel plate capacitor. Okay, not like this one. The difference is this one is more geometrical. Surface area you can calculate, distance you can calculate, but not this one. This one, voltage is not a problem. We can measure voltage by using a voltmeter. But the charge, okay, might be some problem, because you need to use electroscope to measure the charge. To be accurately, it's not that easy to measure the charge on a plate. Okay, so most of the time this is just based on theoretical purposes, but this one is for practical purposes. We're using this one to calculate the C value. Alright, so both will have the same unit, because even though they look different, but the capacitance unit will be farad, like what we discussed just now. Alright, so that is the parallel plate capacitor. Now we did discuss something on this just now. Okay, so we look into more detail on the epsilon R, which we call the relative permittivity. This relative permittivity, okay, is related to the material that you put in between the capacitor. So that concept is called dielectric. Okay, dielectric. So the purpose of dielectric, what is dielectric actually? Dielectric is actually like insulator. Okay, it is insulator. Okay, but insulator in normal sense is that if insulator are not exposed to electric field, there is no realignment of a molecular structure inside the insulator. So this is like an insulator that is not in the electric field. But when you put insulator inside electric field, the molecular arrangement started to change, and that one is called dielectric. Why it is called dielectric? Why the word die? Die means two. Die means two. So dielectric means there is an electric dipole change, positive, negative. So dielectric means insulator that is exposed to electric field. Okay, exposed to electric field that can change the intensity of electric field between the plates, that two plates. Okay, if you have an original electric field, you put some dielectric inside, the electric field can be changed. Okay, so we're going to discuss in detail how the dielectric affect the capacitance value. Okay, so that is the meaning of the dielectric. No? So dielectric actually in short is actually just simply insulator. Okay, just simply insulator. All right. Now we are going to look at how this dielectric affect the value of the capacitance by changing this value. Okay, so dielectric are categorized. Okay, the ability of the dielectric to the ability of dielectric to manipulate to manipulate the electric field is the epsilon r. Okay, the ability of the dielectric to manipulate how it affects the electric field inside there. That value is called the relative permittivity, the epsilon r. Different material have different type of ability. For example, mica is a type of insulator. It has about a value about 3 point something. And then water actually surprisingly have a very high value, but we don't put water in between parallel plate unless you have a very pure water, because water that is contaminated can actually become actually a conductor. Okay, imagine electricity with conductor, they don't mix very well. All right, so we look at how the dielectric actually affect the ability the electric field in between the parallel plate. Okay, let's assume you have two parallel plates which are already connected to the positive and negative terminal, and we have this original electric field already created here. These are the electric field, red color, original, and I will call this one E0, electric field, original electric field. And then this one is without dielectric. Now the second diagram is this. You insert a piece of dielectric field. Okay, dielectric field. Dielectric. So insert a piece of dielectric. What happened here is this insulator have macromolecule that can easily manipulated by the external electric field. So all the molecule will line up. Okay, well, not entirely line up, So they will line up according to the external electric field. So the molecule are huge for most insulator. So the one that is actually lined up to the positive side is the negative part of the molecule. Okay, and this one is the positive part of the molecule. And now because of the line up, it creates its own internal electric field. This is the internal electric field. Okay. And don't forget, we still have our external electric field here. This is our external electric field. Now, our external electric field is E0. Our internal electric field is EI. So, electric field are vectors quantity. Okay, so they can be manipulated. They can be minus. Okay, so that means if you put insulator in between or dielectric in between with a certain thickness, okay, you can actually produce a new electric field which is orange in color. Okay, this one. Okay, the net value. So this is the net electric field. The net electric field is actually equal to the original electric field, E0 minus your internal electric field. Okay, because of the realignment of the molecule for the dielectric. So you see, the value here is is smaller compared to the original electric field. If you put something inside, I mean dielectric inside. So this one can actually reduce the electric field in between the parallel plate. Now this one serves one very important purpose. The purpose is to reduce the spark, okay, the arcing in between the plate. Because if there is no dielectric in between the parallel plate, what happens is if you increase the voltage too high, the air molecule in between will start to be ionized and spark occur. It's just like lightning in the sky, but these are small scale. When the spark occur, they're discharging, so you don't have a concept of capacitor anymore. That is actually some sort like a ionization process, and it's not a very easy way to calculate the capacitance value in that way. Okay, so that is the purpose of dielectric. Alright, so that is the purpose of dielectric, and this is how actually it affects the electric field originally from here, reduced to this value by minusing the internal electric field. Alright, okay. So the next one, for the next topic later, we're going to look at the capacitor network and also the energy stored inside a capacitor. Thank you.